So proving the running time, as I said, is pretty straightforward. So let's just walk through each of the lemmas, right? So there's 3 lemmas, and then eventually we are going to get the theorem, right? So let's focus on focus on the first lemma, right? The first lemma says that there are only 1 plus log c scaling phrases. Scaling phrases basically is really just the number of different deltas we have seen like throughout the whole algorithm, right? Just recall that how do we set up the delta? We set up the delta, the first delta equal to 2 to the k, such that 2 to the k is less than c and k is maximized, right? And in each of the subsequent what's called the scaling phrases, we sort of scale this delta by a half, right? So the second delta we are going to see is 2 to the k minus 1, the third one is 2 to the k minus 2, and so on and so forth. Eventually we will get delta equal to 1, right? So the number of different deltas here is exactly k, right? But also we know that 2 to the k is less than c, right? So we can sort of see that k is log c, right? So this is where this first statement is really talking about, right? So the number of scaling phrases, it's around the order of log c, right? So so the statement here is also one sentence proof here, right? So this is the first statement. And the second statement says that if we look at the flow at the end of the delta scaling phrase, right? So what do I mean by at the end of the delta scaling phrases? That means that if I set delta to be a specific value, say 32, right? So now I'm going to push a number of flows, right? So with the assumption that all the edges that are below 32 are deleted until I cannot push anymore, right? So basically this is the flow we are interested in, right? Right before we have to scale down delta, right? So let's do be this flow, right? So now if we assume that f is the flow that's at the end of the delta scaling phrase, then the max flow is going to be smaller than the value of flow plus m times delta, right? So for this moment, let's just assume this is true, right? So it's going to take a bit of effort to prove this statement here, right? And so now that's the lemma 2. This is basically says that at very high level, what does this lemma says? The lemma says that if we know the flow value and we know the delta, and m here is the number of edges, right? Then we do have a conservative estimate of the optimum solution. The optimum solution will not be larger than our current flow, the value of our current flow, plus m times the delta. Delta is the current delta we are seeing at this moment, right? The lemma 3 basically says that if there are not if there are. So if I count the number of augmentations in each scaling phrase, right? So again, like just recall that a scaling phrase is really just that we fix a delta, we try to find a lot of augmenting passes until we cannot find any more, right? So basically, this lemma says that if I fix a delta, the number of augmentation or the number of augmenting passes I can find is going to be not larger than 2m, right? So let's just explain why this is true, right? So basically this is really just utilizing the lemma 2, right? So let's really just walk through the statement. If we let f to be the flow at the beginning of a delta scaling phrases, right? So let's say that my delta, right? So how can I say that? Like there's a subtlety over here, right? So let's assume that okay, so let me do things in this way, right? So let's assume that at some point my delta is 2 to the k prime, right? So this is at some point this is my delta, right? So this is at the beginning of the scaling phrase, right? So now let's also look into what was happening right before my scaling phrases, right? So before my delta is 2 to the k prime, my delta is actually a double of that, right? So you can really imagine that we start with the delta being very large and then gradually move down to the 2 to the k prime minus 1 plus 1 and then move down 2 to the k prime, right? So this is what's happening here, right? So let's examine what's happening the time period right before here, right? So the time period right at the end of the last phrase really tells us the optimum solution value of the optimum solution is going to be less than equal to value of current flow times 2 times m times delta, right? M times delta. Let me just delete this one, right? M times delta. The delta here is really just that it's the phrase, the previous phrase we are talking about is 2 to the k prime plus 1, right? The current phrase is 2 to the k, right? So it's really just equal to 2 times m times 2 to the k prime, right? This is a bit of algebra manipulation. And there's a definitional issues, right? So the delta here, right? So sometimes it's used as a variable that can be shrinked over the time. Sometimes it's used as a fixed number, right? So if we call 2 to the k prime equal to delta, like we assume that delta is as a fixed number rather than a changing variable over the time, then 2 to the k prime is delta, right? So this is 2 then m times delta, right? That's the reason that in the lemma 2 is m times delta, in the lemma 3 is 2 times delta, 2 times delta. It's really just because the lemma 2 is talking about at the end of delta scaling phrases, which correspond to when delta equal to 2 to the k prime plus 1. And the third lemma is really says that at the beginning of the delta scaling phrases, right? So this is really that we move to the next phrases where delta is k prime, 2 to the k prime, right? In this case, right, so we apply lemma 2, we sort of get to whatever this kind of equality, right? So the equality we are getting here is max flow is less than value of the f we have so far, and m times 2 to the delta, right? So this is what we are copying here, right? So now, with that, right, and also that we sort of know that within the delta scaling phrases, right, so the only point here is that after we delete all the edges, right, so after we delete all the edges that are smaller than delta, whenever we found the augmenting path, the minimum bottleneck would be at least the delta, right? So that basically means that at this moment, my value of flow is we have the value of flow like that, right? Our optimum solution is less than equal to value of the flow plus m times 2 delta, right? And every time you have an increment, right? The increment is at least the delta. Then the number of increment here will really just that by m times 2 delta divided by delta, right? So it's getting a bit messy. So let me just switch back to the whiteboard and then explain this idea again. So let's really just redo the lemma 3, right? So because it has been messy, right? So let's assume that we start with delta equal to 2 to the k, right? So after certain iterations, right? So it becomes 2 to the k prime plus 1, right? So this would be maybe the ith iteration. This is what our delta is, right? So just recall that delta is going to scale down again by half, like in each iteration. So the iterations we are talking about is the same as what they call the scaling phrases, right? And now, so the lemma 2 basically says that if at the end of the scaling phrases where delta equal to 2 to the k prime plus 1, if I look at the flow I have so far, right? So I can sort of, this is my s, this is my t, and this is my flow. If I look at the value of my flow, and if I use this plus m times delta, right? The delta corresponds to the delta here, right? So it's the delta here, right? So this is the 2 to the k prime plus 1, right? Then I know that this quantity is going to be at least going to be larger than the value of the optimum flow, right? So I sort of know that like this is my solution, my flow, my current solution. This is the optimum flow, and I sort of know that this gap is bounded by m times delta, right? So now if I want to, after this is what's claimed in lemma 2, right? So now in lemma 3 we say that let's just because like at the end of, this is really at the end of this particular scaling phrases in which we are not able to do updates anymore, right? So let's just move to the next stage, right? Let's do scaling again, right? In this case, after I scale the delta by half, then I have 2 to the k prime, right? So now I want to look at what's exactly happening at the beginning of the scaling phrase. At the beginning of the scaling phrase, f is not updated. The f in the beginning would be the same as the f in the end of the last scaling phrases, right? So my value of the f remains the same, right? But my delta is half, right? So basically, you can sort of see that at the beginning of a scaling phrase, if I copy everything here, it's what I'm going to get is that the value of the optimum solution is going to be less than or equal to the value of what I have now plus m times 2 to the k prime plus 1, right? So this is just using the fact that in the previous stage, the delta equal to k prime plus 1. This is in the previous stage, right? I can really pull out this plus 1 here. This becomes 2 to the k prime times 2 and value of f, right? This is what we have here, right? So now we sort of also know that the new delta is exactly 2 to the k prime, right? So there are two deltas, right? There's a bit of the overloading of the notations here. But in the new delta, right, so we sort of call this is delta, and there's a 2 here. This is m, and this is the value of f, right? So this is what we have when in the beginning, so when in the beginning of the scaling phrases we are talking about here, right? So I'm not able to move around things, right? So, right. So this is really just, I'm talking about the scaling phrases that's for this particular component, right? For this particular component, I do have this condition here, right? So let me just rewrite the whole thing. Value of f star less than equal to value of f in the beginning of the scaling phrases over here plus 2 times m times delta, where delta equal to 2 to the k prime, right? So this is a new delta, right? So this is the story here. Now, the second thing we're going to do, right? So let's examine let's just focus on the scaling phase. Imagine you have you try to look into the details of this entire scaling phrases. Let me just redraw redraw the whole thing, right? So this is when delta equal to 2 to the k prime, right? So there will be, so we start with some sort of flows, right? So that's flow solution f that's moving from s to t, right? This is the solution that's described here, right? So what we need to do is to find an augmenting path for the graph, what's called the g t delta, and do an update, find another augmenting path, do another update, and so on and so forth, right? Up to the end, right? We will not be able to do any update. Then we move to the next phrase, which is delta equal to delta divided by 2 again, right? So we scale by half, right? So this is like in general what's going to happen in each of the phrases. Now, we are asking the question that how many updates are there, right? So this is what the lemma 3 is talking about. How many updates are there? Updates are there. So the crucial observation is that in any of these iterations, right? So I'm talking about, so if I look at my residual graph, gt of delta, if I look at my residual graph, all the edges has capacity that's at least delta, right? So whenever I find an augmenting passes, then I know the bottleneck is going to be at least the delta, right? So that basically means that whenever I do an update, so let's call this as f prime after the update, then f prime, the value of f prime minus the value of f is going to be at least the delta. Whenever I have an update, the update value has to be at least the delta, right? So so in other words, I'm going to make a progress at least the delta in each of the iteration, another delta, right? But the total amount of progress I can make, right? So let's call this f prime prime double prime, right? So if I look at the f double prime minus f, what would be an upper bound, right? So f double prime will not be larger than the optimum solution, f, right? But the value of f, if we look at the conclusion we have, there's a relationship between the value of the optimum solution and the value of f, right? So I can really just copy the entire whole thing down, right? So can I copy that? Yes, I can copy that, right? So I can copy the whole thing down, right? So I can copy the whole thing down and then see that, right? So I have the value of f, right? So the value of f is not going to, the optimum solution of the f it's not going to be larger. It's going to be smaller than the value of what we have at this moment plus 2 times m times delta, right? So let me just substitute that in, right? It's less than equal to value of f. So this is also value of f, right? Plus 2 times m times delta, right? So basically this term get, let me just this term get expanded in this term, and then I sort of copy this term out, right? Value of f, right? So now there's a cancellation happening, right? So this is the only remaining term, right? So we have the 2m delta, right? So let me just rewrite everything. So everything here is that really that what we are seeing here is that f prime prime minus f is going to be less than equal to 2m delta, right? So this is what's happening at this moment. Let me pause. So now let's just look at this. This quantity is what we get, and let's head back and see how does that help us, right? So let me just again copy the whole thing, copy, and let's see what we are seeing here, right? So we are sort of we are seeing here, right? I cannot really copy those whole thing. It's so messy. So let me just redraw everything. So let me paste back what we have so far, right? So let's see. Let's go back and redraw what we have just now, right? In the beginning of this delta scaling phrases, right? Delta equal to 2 to the k prime. We have an f here, and it corresponds to some flow. And then I do some update, all the way to the end, right? At the end, maybe I have a new flow, right? So this is f double prime, and I cannot do anything more, right? Then I need to go to the next phrase, right? So now I sort of know that the update, each update, we are going to make a progress. That's at least the delta, right? So this is what we saw just now, right? So this is at least the delta, because as I said, we mentioned it just now, because when we are doing the capacity scaling, we delete all the edges whose capacity is less than delta. So the bottleneck throughout the whole phrases will never be less than delta, right? So each time I'm making a progress, at least the delta. And at the same time, f double prime minus f is at most, right, 2 times m times delta, right? Then this implies the number of updates or the number of augmentations that's really written in the slides is going to be at most 2m, right? If this were not true, like just imagine if this were not true, if I have a number of update that's 2m, right, 2m plus 1, and each time my progress is delta, then basically I'm going to come up with a new flow that's at least as large as 2m plus 1 times delta plus value of the flow here, right? This is actually contradict to the fact that f double prime minus f is less than 2m delta, right? So just by a simple proof by contradiction, we know that the number of updates is at most 2m, right? This is basically what the lemma 3 is talking about. So let's switch back, right? So let's focus on, let's just internalize the message here, right? So the number of updates within every single iteration, every single scaling phrase will be not larger than 2m, right? So this is the message that's here. So let's right. So now after we switch back to the slides, this is exactly what we were talking about. If I look at the one scaling phrase, the number of days at least at most 2m, right? So this is the lemma 3. With the first 3 lemma, then we are able to prove the running time of here, right? So basically, the major running time theorem is that the capacity scaling algorithm's running time is going to be m squared times log c. M is the number of edges, right? So if we have this kind of running time, then this is going to polynomial in the input size. Then this is what we call the efficient, right? So now it's really just the invocation of the lemmas we have so far, right? So the total number of scaling phrases is log c, right? And for each of the scaling phrases, we have m augmentations, right? Then the total number of augmentations across all scaling phrases would really just be the m times log c. And the finding an augmenting path is going to take order of m time, right? So this is because we can find the ST connectivity by using the BFS of DFS, right? So this is linear, right? So basically at the end, if you just take the product of these two terms, then you will get the running time out, right? So by now we sort of see the entire outline of the running time analysis. The only thing we haven't seen, right? So there's a question mark here, right? So the only thing we haven't seen is lemma 2. So let me just delete everything and let's look at what we are talking about in lemma 2, right? So lemma 2 says that if I look at a particular flow at the end of the scaling phase, I'm able to give an upper bound of the optimum flow in terms of the flow I have so far plus m times delta. So now let's move to prove the last bit of the whole theorem, the whole analysis, right? So the lemma 2 says that let f to be the flow at the end of the delta scaling phases, then I have an upper bound on the maximum flow in terms of the value we have so far, the number of edges, and the delta, right? So our proof really just needs to find a cut such that the capacity of the cut is at most the value of our current flow plus m times delta. Right? So now by using the weak duality we did in the last lecture, we sort of know that the capacity of any cut is an upper bound of the value of the maximum flow, right? So by showing this one, then we are able to show that the optimal solution, the max flow is going to be less than value of f plus m times delta. So now again, like the procedure is almost identical to what we have for proving the max flow min cut theorems, right? We look at the graph, the GF of delta. Basically, this is the residual graph minus all the edges whose capacity is less than delta, right? So this is the definition of GF of delta, right? So now we start with a GF of delta, and we run a BFS, and starting from S, and find all the nodes that are reachable from S in the GF of delta. And let's call this set of A, right? So this is almost identical, right? This is it's when we do this kind of max flow min cut theorem, right? We have been using this we have been trying to construct A and B in this way for multiple times, right? So why not just do that one extra times, right? So, but this time it's on GF of delta, right? So GF of delta is, let me just repeat, it's really just the original residual graph minus all the edges whose capacity is less than delta, right? Right. So now again, when we have the S set, A set, we really have two properties. The first property is that S belongs to A because we start a search from S. The second property is that T doesn't belong to A, otherwise we can still find the augmenting path. This is not the end of the delta scaling phase. So the definition of the delta scaling phase really means that we can no longer do the update, right? So that means that T is not in A. Right. So now let's just walk through a little bit of math over here, right? So this is the really final piece of puzzle we need to tackle, right? So this is the value of f, right? So this is the capacity of A and B, and minus m times delta, right? So in case we manage to establish the whole inequality, then we know that the capacity of A and B is less than value of f plus m times delta, right? So basically, by just looking the conclusion of this block, then this is what we need, right? So now we really just need to walk through how can we come to this conclusion, right? So now let's just walk through each of the inequalities or equalities one by one. The first equality basically is really just the flow value lemma, right? So the way we count the value of f is really just that we count all the edges that are going out of A, all the flow that's going out of A, and minus all the flow that are getting into A, right? So this is one of the major building block we proved in the last lecture, right? Now this is the first part, right? So the first line is pretty straightforward. It's, as I mentioned, it's really just it's also highlighted by the lecture notes. It's the flow value lemma, right? So now let's really just look into whether we can get an upper bound on that, right? So let's just look into how can we move from the equality to here, right? So now for the second inequality, it gets a bit it's also straightforward, but we need to be a bit careful, right? So the second inequality basically says that if I look at this component, right, I do a component-wise comparison, right? Let me just erase whatever that's here, right? So, the here what we need to show is that for each of E that's out of A, Fe is always at least as large as C to the E minus delta, right? So component wise, it's at least as large as that, right? So for each of the component within the sum, the Fe is small, at least as large as C to the E, C of E minus delta. Then when I sum up everything, then this component, the sum is at least as large as the sum of everything, right? And similarly, we can apply similar argument to prove to show that there are some component-wise the relationship between f of E and delta, right? F of E, so really just recall what are we talking about? F of E is the current flow, right? And the C of E is the capacity, the original capacity of the edge, right? So we sort of need to establish the component-wise the relationship. And let's just switch back to the. It's getting a bit busy for this slide, so let's switch back to the whiteboard to explain why. Right. So let's recall what we have now, right? So we have a graph that's called G of f of delta, right? So basically it's an arbitrary graph, right? So and there's an S, there's a T, right? Based on the G of f of delta, then I'm going to find a set of A that are reachable from S, right? So this is the set of A, right? So and then the rest of them would be the set of B, right? And I'm going to right. So what we did is the value of f is equal to the E out of A, the flow of E minus E inside A flow of E, right? So now let's just pay a bit of attention here. So we are really playing with two graphs at the same time, right? The first graph of G of f delta is with some edges that are deleting some edges with capacity that's less than delta, right? But when we use the flow value lemma, we sort of really just need to go back to the original graph G, right? So when we look at the flow value lemma, what we care about is the original graph G and the existing flow, right? The existing flow, right? So this is the flow, and this is the original graph G, and we need to sort of put aside the G of f of delta at this moment, right? So when we talk about the E out of A, it's with respect to the original graph, right? This is one thing we need to pay attention to, right? So now we sort of want to claim is that f of E is at least as large of the C of E minus delta, right? So if I look at any A and any B, and then if I look at one flow that's going out from A to B, right? So there's a f of E, and there's also a C of E here. Let me just change the color, right? So let's call that the C of E is a different number, right? So now let's even be more concrete, right? So let's call the f of E is going to be 10 and C of E is going to be 15, right? So now I'm going to claim that the f of E is going to be at least as large as C of E minus delta, which means that I'm going to claim that 10 is be at least as large as 15 minus delta. And why is that? So if I look at the augmenting path, right? So if I look at so now I have this kind of flow, right? If we look back to the path, the graph at G of f of delta, if we look back at this graph, how can we construct that? So the construction is really using two steps. The first step is really construct the residual graph, right? The second step is to delete all the edges with capacity delta, right? So in the first step, what's going to happen? It's going to happen is that just call this two nodes as U and V, right? U and V, right? So U and V, like I'm going to construct the residual graph. The residual graph, the forward capacity will really just be C of E minus F of E. The backward capacity would be F of E, right? But this is irrelevant, right? Now, when I sort of delete that, right? So when I want to delete the edges, the claim is that the UV edge is deleted after the second step, right? So basically, I'm saying that when I look at the residual graph, then the U to V is over there. Sometimes it's over there, but maybe it's already full. But it's possible it's over there. But after I really delete all the capacity that's less than delta, the edge here is not supposed to exist. U and V doesn't exist anymore. Why is that? If U and V exist in this graph G of F delta, then V would really just be reachable from S. Right? Why is that? Because now just remember that the way I construct A is really just that I start with the graph of GFF delta, and I start with S, I do a BFS, and then I find all the nodes that are reachable from S, right? So there's a U over here, right? If there were an edge that's connecting between U and V, then if there's an edge that's connecting between U and V in GF of delta, right, then the edge is presented here, right? So we already know that we are able to reach from S to U in the GF of delta graph, right? And together with the fact that the U and V is an edge of the G of F delta graph, then that basically implies I'm also able to reach from S to V by using S to U and U to V, right? But then by our definition, right, we sort of assume that this edge is the crossing edge, right? So the fact that we are considering this edge is because that this is an edge we believe is E out of A, right? E out of A's definition is that U is in A and V is not in A, right? This is contradicting to the fact to what we are getting here, right? So in case, right, this edge is presented in the GF delta, then V will also be part of A, then E will not be out of A, right? Then we shouldn't be considering this edge at all, right? So the fact that we are considering this edge is really just implying U and V is not in G of delta, right? So let's pause a bit because I have